So today's session is about introducing you to mathematical logic. Mathematical logic is about taking statements and converting those statements to symbols and then applying logical deduction to those symbols. And to be able to do this, really we have to begin by learning the language of logic. All logic is based on propositions. Now propositions are statements that can be either true or false. And it's really important that we know what propositions are not. They are not comments, they are not opinions, and they are not questions. If we have a look here, I've got three things here. A hexagon has 6 sides. That is a proposition, and this proposition happens to be true. A hexagon does have 6 sides. This is a proposition. A hexagon has 5 sides. It's a statement, but this statement happens to be false. So we've got a proposition that is true, a proposition that is false, and finally we've got the French language is difficult to learn. Now that is an indeterminate comment because people learning the French language, there'll be no common opinion that the French language is difficult. Some people will find it easy, some people will find it harder. So it's not a proposition. And as usual in mathematics, we use letters to represent our propositions. So in this case, our proposition P, with our colon, is that it is snowing. So if that's our proposition, the negation, or the opposite of our proposition, is that it is not snowing. And we represent that by using this symbol here, and it actually looks like a negative sign, with a little drop down at the end. So that is the negation of P. So P is it is snowing, the negation of P is it is not snowing. And we also have to note that the negation of P is P, really similar to negative numbers, 2 negatives making a positive. All right, let's go on. So every proposition must take a value of either true or false. And we represent those possibilities and those outcomes by looking at a truth table. For our proposition P, it is snowing, there are 2 options. It can either be true or false. That's what a proposition is. It has a possible true or possible false. The negation of P then is the opposite of what P is. So if P is true, the negation of P is going to be false. If our proposition P is false, then our negation is going to be true. It's the opposite. And just following it through, well, the negation of our negation. So the opposite of false is true, and our opposite of true is false. So this is the truth table for the negation of P. Let's go back to just the negation of P. We can represent this on a Venn diagram. So if we have got our universal set, and P is a set inside that. So P is the set whose elements have the characteristics of our proposition. So if that's P, then the negation of P is everything that P isn't. So all this area. So in set notation, the negation of P is P dash. So that's your set notation, and this is your logic notation. We've talked about a single proposition, but more often than not, we've got more than one to deal with. And so we're moving into the field of compound propositions. And they're normally joined up with connectives such as and or. So we're going to have a look at those. The first one we're going to talk about is the conjunction. The conjunction, and that's the and statement. So if we've got 2 propositions, one P and one Q, the conjunction is P and Q. And what that means is the result of the proposition of the conjunction P and Q, the result is only true when both propositions are true. How do I remember this? Well, this sort of upside down V here looks a bit like a capital and. So the conjunction of P and Q, that's how I remember it, that the conjunction is only true when P and Q are true. So let's have a look at the truth table for that. What did we say? This is we're considering the conjunction here, the conjunction of P and Q. And we said that it's only true when both P and Q are true. All the other options, true, false, false, true, and false, false, are going to be false as well. At this point, I just want to look at this truth table as well. This is your standard truth table. These are all the possible combinations that you have when you've got two conjunctions. And the way I go about it is thinking you're trying to get as many truths in the table to begin with. So true, true. Keep your P true, make the other one false. Then we've got two falses, true and a false. We're going to set up our truth tables that way every time. So, the truth table for the conjunction P and Q is true, false, false, true. Remember, that looks like an and, so it's only true when P and Q are true. So let's look at the Venn diagram then for conjunction. So we're looking at the Venn diagram for P and Q, P conjunction Q. So this time we've got our two sets. It's Q and P. And it's only true when both P and Q are true. That means it's just represented by that section there. So that represents P and Q, the conjunction P and Q. Can you remember how we write that using set notation? That is the intersection of P and Q. Very similar as well, it's the intersection of P and Q. That's your logic language. That's your set notation. Right, there's a couple more to consider. The next type we're going to look at is disjunction. There are two types. We're going to consider the inclusive one first of all. Now this is true when one or other or both propositions are true. How do we remember that? Well, I think of it like this. That looks like a bit like this inclusive disjunction symbol looks a bit like a blown out umbrella when it's been blown out by the wind. Now, in a storm it's good to have an umbrella. It's also good to have gumboots. It is even better to have both. So if you've got an umbrella, that's good. If you've got gumboots, it's good. And if you've got both, it's also good. What do I mean by that? Well, look, if I've got any true at all, if I've got P represents my umbrella, Q represents my gumboots, I can have one or other or both. So, umbrella, gumboots, great, true. My inclusive disjunction is going to be true. I've got an umbrella but no gumboots, that's okay, it's still true because I've got one or other. False, true, so that's no umbrella but gumboots, true. So the only outcome that is false is when you've got no umbrella, no gumboots. False. A little bit silly, but it helps me to remember it. So we've got the truth table for the inclusive disjunction of P and Q. Let's look at the Venn diagram. Okay, so inclusive disjunction is what we're looking at. We said that we get a true in our truth table if it's P or Q or both. So it's all those areas there. And if we're thinking about our set notation, how do we represent that in set notation? Well, it's the union. P, union, Q. Everything in P, everything in Q, and everything in both. So we've done inclusive disjunction. We want to do exclusive disjunction, and I don't know if you can see very clearly, but there is a line underneath this symbol here. This is true when one or other of the propositions are true, but not both. How do I go about this? Well, this looks like, to me, a cup and a plate. Now, after all the earthquakes, I don't have much crockery left that's intact. So if you come to my house, you can either have a cup or a plate, but I haven't got enough for you to have both. So, how do we link that to our truth table? Well, if we imagine our P is having a cup and Q is having a plate, with the exclusive disjunction, I can have one or the other but not both. Here, I'm trying to have a cup and a plate, so I can't have that, so that's false. Here, I've got a cup but no plate, so that's okay. Plate but no cup, that's okay. And that has neither one nor the other, so that must be false as well. So our truth table for our exclusive disjunction is false, true, true, false. So that's when one or other of the propositions are true, but not both. Cup or saucer, or cup or plate, but not both. And let's just have a look at the Venn diagram. Again, we've got our two sets P and Q. So it can be P, we can have one of them, or the other, but not both. So this region in the overlap here is not included. And just as we come to the end of this first session, there is a little bit more language that I want to consider. A logical equivalence is if two compound propositions have got the same final column in your truth table. And here are two really commonly used results, which are called De Morgan's properties. And what we've got here is the negation of the conjunction of P and Q is equal to the negation of P with the inclusive disjunction, the negation of Q. Those two are the same. And similarly, we've got this as well. I'm not going to dwell on that now, but actually you could prove that using truth tables. And that's something we're going to be considering in the next session. So logical equivalence, when they've got two compound propositions that have got the same final column in your truth table. A tautology is if with your compound propositions, your final column in your truth table is all true. A tautology is all true. A logical contradiction, on the other hand, is the opposite of our tautology. It's when that final column in your truth table is all false. All true, tautology. All false is a logical contradiction. And that's the end of our session.